So, what we assumed in the previous case is you have a PL cube by 3 EI as displacement, or it could have been some classical stuff that you talk about, right. Let us say that you did not have them, or this is a complex cantilever beam that I do not have a closed form solution. But my problem requirement says that I need to meet some displacement constraints, or I need to meet some stress constraints, and obviously our goal is to reduce weight in this case, or it could be the other way around. I want to reduce stress. You are building a space structure, you are not worried about cost, you are worried about weight though, you are not worried about cost. So, material selection could be the highest material that you can build. I want less stress on it, I want less deflection in it, I want less heat emission in a cell phone device that you are doing, more usage, but I want less heat dissipation. Okay. And the 3 examples that I just quickly told you, like the space structure, the cell phone, you do not have a closed form solution like this, but you need to be able to compute your stresses or displacement. How can you do that? As we have n number of times we discussed, we can use a computer model to do this, right. But the computer model, as we just saw now, what it does, it tells you please give me a set of input variables, which is nothing but your design variables, and I will give you a response y, correct. But it does it only for one variable, please understand, one combination of your design variable. For the sake of discussion, we will say L and I are the design variables. Okay. Then you feed this guy to the computer model, it will give you a y, that is all, that is it. If you change this L and I, you will have to redo the computer model, it will give you another y, correct. So, every time I have a new L and new E, I need to go plug it in, and then it will give me a new delta. So, in this case we just call it y in general. Okay. But what happens if this computer model is very expensive, very expensive? Expensive means in terms of time. Okay. Imagine that it is a very complex cantilever beam. Okay. Cantilever beam cannot be complex beyond it is a complex structure. Okay. So, it takes about, today if people want to do some kind of an aerodynamic study, okay, which mimics a wind tunnel, okay, in a cluster, not our cluster, in an industrial cluster, it takes 4 days for one combination. Okay. Even some crash studies, in our cluster we run one crash study takes about overnight, and you know, right, that overnight is not just overnight, you have waited for 4 days and then you get an overnight. Okay, because there are 599 other faculty who are also competing for the same resource. So, you will have to look it up from that sense, you cannot just say okay it is only 12 hours, no, it is actually 48 hours or maybe more than that, not 48. Okay. For example, I am saying one simulation waiting time is 32 hours and then 18 hours for running the simulation. So, it is 50 hours actually. Okay. That is just to give you an idea. Let us not worry about the waiting period. Okay. So, when I said expensive, it means that computational time, but computational time is related to your cost. It is a cost because you need computer facility, waiting time, everything, because in the industry it becomes very important. I cannot wait for 100 days. Because my product release time itself is only 3 months. I cannot wait for 100 days for you to get all the simulations. Okay, anyway, so we are slightly digressing, but the question is, if this is expensive, what would you like to do? You would like to have something like this, like this. Okay. So, the question is, can I relate, if I would call these design variables as x, can I relate this x and y? that is what the question is. So, this x when I am writing it as a vector, it means x1, x2, x3, but they could have multiple values of x1, x2, x3. Okay. It should actually be written as a matrix in that sense. Okay. Similarly, the y is not a vector, it is not only y, it could be y1, y2, y3. Okay. So, you usually write it as, okay, we write it as y equals f of x. The question is, can I approximate this f? So, right now what we are in the regular cantilever beam problem that we are talking about. So, your y is your delta, you are saying it is a function of P L comma E comma I, that is what it is. Okay. This equation P L cube by 3 E I is the f, but you do not have this equation, then you go to the help of computer model. Okay. Then you want to approximate this f. So, f hat, it is not or f tilde, okay. It is an approximation, it is not the regular f. So, can I approximate it? How do I go about approximating? How can I approximate?
Some factors.
Sorry?
Using some factors.
Some factors. Okay. In a simple sense, what is happening is, let us say 1D problem. 1D problem, I have some x, I have some y. I just gave you 3 points, okay, and I am asking, can you, is very difficult, okay, this data, okay, through a complex process I have gotten this x and y, okay, but I am saying that this takes about 4 days for each of the entry. I have spent 12 days to get this data. Is there an easier way, so that I want for 2.2, can you tell me what the value is? Is it possible for you to do this? This is the question. Okay. So, what is the goal? I mean, what is my goal is, can you find a relationship, this f can you find? So, what it means is, you give me a new x, I will give you the new y. Okay. You cannot say, sir, you got this x and y, why do not you go and find? Yes, it will take 4 days, but can you give it to me in few seconds? Can you give me a closed form solution? And that need not be the exact. See, please understand, when you try to reconstruct this guy, you might not end up reconstructing the same equation. You might get something like PL raised to 2.8 divided by 3I raised to 1.1. You might get something like that, because that is based on data, and the data could have errors. Actually, as a matter of fact, I should do it like this. This should have been the data, because there is always some measurement errors or some other factors that influence. Okay. So, if you look at it, since I wrote it the first way, the way that I wrote it was y equals 2x, that is what I wrote. Okay. But I introduced some errors, so that when you try to construct this f, you will not get it as 2 times x, you might get something else, you might get 2.1x or 1.9x, whatever it is, you will get. Okay. One simple way is just try looking at it, it's not necessary. One way when you have data is to plot them. Okay. The moment I say this, most of the people answer the question. Okay. So, 2.2 means it was somewhere here, then 4.1 is somewhere here, 5.6 will be somewhere here. This is the type of data that you have. The red circles are the data. Okay. Now, I am asking, can you tell me at 2.2 what will be the value of y? How can you find it?
By interpolation.
Okay. Now, I change my mind, and then I am asking for, can you tell me for 3.6 what the value is?
So, making a graph and then at that point where the graph intersects.
Okay. So, how will you go about graphing? But one second, let me go back to the question that I asked him. So, 2.2 you said that you will interpolate between these two values and you will find it, but then I changed my mind. because we are professors, right. So, what we will do is this, I will suddenly ask 3.6. What will you do? You will again go and interpolate, and you know that I am going to give you 100 such questions. So, every time you will go and interpolate. It is interpolation, but you will have to do a wise interpolation. That kind of takes a form that he says. What is that you will do?
So we will make a graph joining the points.
You will make the graph joining the point, but there I can join them multiple ways. So, one is like this. Now, you decide how I want to connect the other one, just like this. There is some mathematical issues when I do this,
You should find the relation between a y and x.
and that is the overall goal, correct. That is the overall goal. I am just trying to help you. I am just trying to help you to go towards that. You are absolutely right. That is the overall idea. Because the moment you have y equals 2 times x, it is simple, right. I give you the x, you can find what the y is. But how do you know it is 2, it is not 3, it is not 1.8, it is not 1.4. So, this is please understand, this is not necessarily the way to go about it. I just plotted. And then I am asking, I thought that it might give you some indicators to do that, okay. I am not saying that this is the way to do it, okay. So, if you do like this, there is some issues with the function itself, okay, about continuity and all that, okay. So, what might be the way to do it? So, one way to look at it very simply is, you look for, as he pointed out, I want to approximate the function y equal to x. So, one simple question is, how does this data look like? I know it does not fall in a straight line, but it is pretty close to a straight line that I would draw. Straight line means not a flat line, but a line like this. Just trying to make sure that I am not putting a light color. There could be other questions. Why did you choose this? Can't you choose this? Yes, I will choose. There is an alternative. This is what I told you. There is an alternative. Okay. The question is, how will I choose which curve I will take? I can write, I can draw like million curves here with these 3 points. Million is just a number to tell you that there are a lot of curves that I can draw. Okay.
Least square method.
Sorry?
Least square method.
So, there is a method called the least square, okay, least square fit, which we will discuss when you go to something called polynomial response surface. Okay. So, you choose that. So, I just wanted to expose you to a problem. Okay. You will use some kind of a method that says that need not go through all the points, because as I pointed out, there is always error in these numbers themselves. So, you want to do something called a best fit. That best is the criteria that you choose. For him, the best was battery backup. For him, the best was aesthetics. For someone, the best was the selfie camera. So, the best differs, but for him that was the best fit, for him that was the other one was the best fit. Okay. So, the best is what your criteria is, right. So, the criteria allows you to take you towards the goal, or let us call the evaluation criteria. I do not know whether how good is this. I will say the design model kind of takes you to your decision making. In whichever field you are looking at, this is what we are looking at. You are interested in making a decision. If you are a metallurgist, you want to know what material model I want to use, that is a decision making, for which you need to have a design model, which is a finite element, or an experimental model that will give you some values for different conditions of stress or strain, and appropriately you need to have an evaluation criteria. What is it that I am looking at? I am not interested in the elastic zone, I am interested only in the plastic zone, and I am looking for a second order representation, I am looking for a bilinear model, I am looking for a Cook's model kind of a representation. Is it an exponential model? Is it a generalized Pareto model? So, I would use something like that. So, whatever is the evaluation criteria, then I make my decision based on that. Okay. So, this is the overall idea, but in this sometimes your design model is what we are talking about. The design also comprises your analysis, right. I will not have, if you give me a new set of x, it should generate a y, new set of y, so that I can evaluate that particular criteria. So, I need to have an f. I might not have an f explicitly all the time. Then I need to construct that f. This is what we just discussed just now. Okay. A simple, you can just call this line as y equal to mx plus c, then you just need to find your m and c, because x and y is something that you already have. That is the simplest way of looking at it. Okay. The moment I make this into a n dimension problem, this is not a line anymore, it becomes a surface. So, you need to find a surface that will fit, that will run through the points. Okay. Of course, I have other points as well. Okay. It is just not a projection. Okay. So, this f that you are going to construct, this guy that we did just now, is what we call the surrogate, because it is not the actual function, it is only a f hat. It is a surrogate to f, but f is ideal. What I call in my course is, this is God given, that is all. If God comes and asks you, what do you want? You ask for, should ask for f. Okay. Then later you will know why you should not ask for an f. Okay. If God comes and asks you, you are trying to do an optimization, He comes and says, I will give you one wish, what do you want? You say, boss, please give me f. Job is solved. Okay. You do not need to spend 4 hours, 4 days to run simulations at different points. F is there, your job is solved from whatever we have seen as of now, correct? Agree? Fine. Okay, so that is a H and this is the D. So, the reason that we are going to discuss this problem is I will introduce the formal way of casting an optimization problem. Okay. So, what I am interested in this one is, I want to design such a cylindrical structure such that it will hold at least 400 ml, right, yeah, 400 ml content, water, any soft drink that you want. I want to minimize obviously the cost, the manufacturing cost. Yeah. So, some shipping and aesthetics, etc., impose some constraints which are on the design variables. Okay. They cannot vary between, they cannot vary beyond 3.5 or 8 centimeters. Similarly, H also cannot vary beyond 8 and 18. This is your problem. I would not say statement, this is what you are looking at. Okay. Now, how will you cast this as a math? In mathematically, how will you do that? How will you convert these stuff that I have told you or I have given you in a mathematical sense? When you say hold at least 400 ml, what does that mean? Volume of this guy. Okay. So, let us first write what that is. So, volume. And I want to minimize the cost, let me say manufacturing, and it is in this particular case directly related to material, let us say the amount of material that you are using. Okay. Do not think too much on the machining or the laser and all that. When I say cost, it is only the material cost that we are talking about. How will you go about evaluating the material that is required for making this? Okay. Thickness is there, but let us say it is constant thickness. So, that is not a variable. So, it is surface area. Okay. Correct. Thickness is one thing, but if I am going to use a 3 mm or a 5 mm, I will use the same across. So, what will matter is what is the length and width or what is the diameter of the thing that I did. Okay. So, what is the surface area of this guy? Sorry, what is the volume? Pi? Let us do it in D. So, that because D is the variable here we use pi d squared pi d squared by 4, that is all into h. Okay. Then what about your surface area?
Pi d h plus the 2 pi 2
Okay, 1 at a time. What is it? Pi
2 pi d
pi d h
plus 2 pi d square by 2
pi d squared by.
2.
Do you know how this came?
2 into 2.
Because the area is pi d squared by 4, but I have a top surface and I have a bottom surface. Okay. Hence, 2 times pi d squared by 4 become pi d squared by 2, and this pi d h is d times h is your rectangle, but of course, since it is a cylinder, I just take the pi into account. So, it becomes pi d h. So, it is a surface area of the cylinder that we are talking about. Okay. Okay, great. Now, you are in this case you know all this, okay. But again let us say that it was a complex tank, you do not know that, then you will have to build a CAD model and then CAD will give you the volume, which is essentially it is breaking it into known volumes, that is all. Okay. Anyway, let us not worry about that part. Now, how will you, because you have just got the quantities. So, you give me a nu d nu h, I will get the volume, you give me a nu d nu h, I will get the surface area. So, what are these called? This just satisfies the analysis part. You understood, right? These equations are nothing but the analysis part. You give me a nu d and h, I will give you the new volume and the surface area, okay. Which means you give me another nu d and h, I will give you another. So, there is an alternative, okay. I can alternate. See, one is it could be fat and it could be short for the same volume, or it could be slender, okay, slender and long for the same volume, okay, or you can get a trade off between the two. So, basically by increasing decreasing d and h for the same value I can get multiple combinations as well. So, now which one will I choose? That is called your criteria. What is your criteria in this particular case? It says you want to minimize your cost, which is your goal primarily, and it should hold at least 400 ml. Okay. See, there could be multiple solutions also just now as we pointed out, correct, but it is also governed by this requirement. I want to maximize the data storage capability on my cell phone. Okay. Go get a, what is the latest phone name? iPhone, what is it? OnePlus, OnePlus, or yesterday I saw some Nokia, some 50,000 rupees, 59,000 rupees. Okay. They might have, but today storage has become cloud. But let us say something else, speed or battery backup, something like that. Okay. I want to maximize, but then I cannot get a like a 60,000 worth phone. So, either if time is there, you wait for a sale, otherwise what do you do? So, you say there is a constraint. So, the cost should be less than 30K. In that, tell me what I will get. Okay. So, you will have to compromise a little bit. So, that maximization is based on the constraint that you have. Okay. So, now whether it is a slender or fat is governed by these guys. Now, we want to cast this into a proper scientific or mathematical, not scientific, mathematical way of doing it. So, how would we write it in a general optimization senses? I want to minimize, you want to minimize your cost. So, I am just verbally writing it first, okay, and that is nothing but let us do it parallelly. That is nothing but your surface area, which is pi d h plus pi d squared by 2. What are my design variables? D and h. This is how it is written, minimize, underneath that your design variables and what is your objective function. This guy is entirely called your so, if you go to departments like management and all that, it is usually called a cost function. We can also call it as a cost function because eventually it will relate only to cost, okay, such that what is my constraint here? Volume should hold at least 400 ml. How will you write that? At least means 400 is okay, if you give more I am happy, it should hold at least 400. Okay. What is the cutoff? This is basically the cutoff. What is the cutoff? The minimal you need to have is 80. You get 85, yes, you will be there, but you need to have a minimum of 80 to get in. So, such that my volume is greater than or equal, this sign is very important, 400. Fine. So, you just need to plug in your equation here for this particular case. Do not get into complex conversions, okay. So, it is either centimeter or meter, okay. So, I need to just, okay, to make it generic I will put the units here, okay. So, you want to minimize the cost such that this is done, okay. So, this is the basic problem formulation, but now how are you going to solve this? It is all good, you have written it in a standard optimization format and all that. Sorry, design variables are here D and H. Oh, correct, there is some bounds also are there, correct, sorry, those are also constraints, correct, such that the D cannot vary this is your problem formulation. Now, how will you go about solving this formulation? We came from the verbal statement to some what I call the mathematical, okay. There are more numbers in this formulation compared to this statement, okay. So, this is all, this is how you write, this is the global way of writing an optimization problem. You write this problem statement, any engineer who practices optimization will understand, okay. They might not understand your cost or volume, but for sure they will understand the equations that you have written, the way that you have done this, okay. This is how it is usually done, okay. To be more precise, you might want to bring 400 to the other side and then say less than or equal to, because always those constraints are written that way. What are those constraints called? Any idea? These are called inequality constraints, okay. If I said please come up with a design that gives you exactly 400, then I will replace this inequality by an equal to sign, then it becomes a equality constraint. So, usually your constraints are equality constraint, inequality constraint, sometimes you call these bounds, which are usually the geometric bounds, or it could be other bounds also, cost, some bounds it could be, okay. You could, because you can also recast this problem if you want. You can say I want to maximize volume such that the cost is less than some value, you can recast that problem that way also, okay. So, it depends what your constraint. So, you also have bounds, we usually call functional constraints, these are called functional constraints, these are just geometric or static constraints, okay. Equality, inequality constraint are the most widely used criteria, I mean terminologies, okay. And this kind of equations where you have quadratic or anything more than that or anything greater than linear is called a nonlinear formulation. The formulation, the equations are nonlinear, okay. Instead, if you had just a linear equation, okay, d plus h such that 2d plus 3h should be less than something, 4d plus 1h should be greater than something, that is called linear programming, okay, LP problems. If you go to management operations research, most of the problem that they solve is linear programming, okay, which means your objective function and your constraints are linear in nature, okay. So, please understand there is a distinction between linear regression and linear, because we are going to extensively use regression, okay. Here the equation itself should be linear, then it is called linear programming. This is a very simple case, non-linear. So, NLP, non-linear programming, okay. So, non-linear functions, that is what we are using, okay. LP problem and non-linear problems, and then equality constraint, inequality constraints, then what? There is a concept of design domain, Okay. So, in this case what are your design variables? So, it need not be a rectangle or a square, but in this case it is. D is one variable and H is one variable. It is going to vary between D varies between 3.5 and 8 and H varies between 8 and 18. Now, in this design space you can get something called the feasible domain, okay, that is governed by what? Constraint. Okay. So, if you can, because now right now with just these two constraints this is the feasible domain. What I have here is what the feasible domain is just with these two constraints. Okay. If I draw the contour of the volume on top of this guy, okay, I know wherever it is greater than 400 my optima will lie only in that. Okay. It is likely to lie on the curve, but it will lie only on the other side of it. Okay. So, that is called the feasible domain. Okay. And what else? Okay. So, in terms of your design variables, usually we try to have them independent, and most of the time they are independent. Okay. Even when you write y equals f of x, they say y is a dependent variable, of course, because as you change x it will change. However sensitive it is, okay. For x1 it might be very sensitive, for x5 it might not be that sensitive, but still it is sensitive. So, y is a dependent variable and x's are independent variables, and your design variables are your independent variables. Okay. So, usually people are very careful with the design variables because they define the dimension of your problem, the degrees of freedom of your problem. Okay. So, when they say the optimization problem is very complex, they ask, oh, you do not know the function? Yes, I have ways to approximate the function. They ask what is the dimension of the problem. Okay. Today it again varies between departments. You go and say in computer science I am solving a 20 design variable problem, it is very difficult, they will laugh, because their design variables are all in hundreds and thousands, they solve these networking problems. Okay. But anyway, the quality of the problem, and not the quality, the type of the problem that you solve are different, but usually we define it this way. In the context of design problems, even 15 dimensions is large, okay. But today people are trying to solve 35-40 dimension problems, it is difficult. Usually run, if you are single digit it is okay, okay, it is a good number. Okay. So, those are the things about design variables, but actually when you plug in the design variables you should be able to get an f. So, preferably numerical in nature, it could be integer, it could be continuous variables, or it can also be categorical variables sometimes. You cannot have, for instance, I, okay. Instead of giving you I can say, can you tell me what is the type of I? So, what happens is 1 is triangular, 2 is circular, 3 is hollow beam. Okay. So, it is going to be categorical. So, if you put 1 it means that it, or you can call it ABC, 1 means it is still numerical, right. ABC you can call it, A is this, B is that, C is that. So, you will have to make a decision based on that, meaning if you put A it means that it is a circular one and appropriately you will use your I. Okay. So, that is the point, and accordingly your problem will be casted, it will change, you cannot just use I directly, you will have to use how do you compare this I with that I. So, there should be something like a bounding variable, and then what is the best one that you will take out of it, because still your objective function might be to minimize your cost. Okay. Okay. So, this is how we write the simple optimization problem stuff. I am just trying to make sure, yeah, these are also called sizing constraints. We call it as bounds or sizing constraints. Okay. Okay, fine. So, this is just to get you started on this stuff.